Hi, welcome to this first online lecture in the Data Analytics for Social Sciences course. This will take us both a little getting used to, but hopefully this works well. In the past few weeks before the break, we were talking about linear regression and logistic regression. The first in the data science literature falls under the regression methods, where the dependent variable, the variable we're trying to explain or predict, is a scale variable, while logistic regression and discriminant analysis, they fall under the classification methods in data science, where the target is to predict the category in which a particular observation falls, either in a binary variable or in a categorical, nominal, ordinal variable. We have only talked about binary variables, but extensions are possible in logistic regression and in discriminant analysis to deal with multiple categories. While logistic regression and linear regression are very common throughout the social sciences, they are perhaps the workhorses of statistical analysis in the social sciences, and they're often used for more causal inference instead of predictive inference. We are now going to turn to a tool that is really specific to the data science machine learning literature, and that is still very uncommon in the social sciences. And this is the tree-based models and the random forest models. And just like with regression, we have classification and regression versions of this. So we have regression trees, where the dependent variable is a scale variable, and we have classification trees, where the dependent variable is a categorical variable that can be in multiple categories. We are going to primarily look at classification trees because they're a little bit easier to follow. Random forest is then an extension that will follow after this in a separate lecture, and they are, as you would guess from the name, sets of trees, and I will explain then when we get to it why that is helpful. Okay, let me switch to the slides instead of looking. So this first section will be about regression trees and classification trees. And as I said, this example is about classification trees. So trees are a straightforward statistical method to use a set of independent variables to predict some outcome variable. So we will look at the following, first, as I said, a similar approach can be done with logistic regression, which is also about predicting a binary or a categorical variable. And they are more common also because of their abilities in causal inference. And this is simply an alternative method. And you will remember that in the examples that we give last time, in the logistic regression and in the discriminant analysis, that it was always about estimating some kind of line or set of lines through the space of all these variables that separates the observations in one class from the other. But as you will see, in many cases, such a line is not a perfect way to classify. Take, for example, this randomly generated data. So we have two variables that we're interested to explain, variable 1 and variable 2. Perhaps they have to do with economic performance or ethnic fractionalization or anything variable that might be interesting to explain whether a country is democratic or not. And imagine we have two kinds of countries, democracies and non-democracies. And as you can see here, all the democracies are in variable 1 somewhere in the middle, neither high nor low, and on variable 2 at the bottom. Right? So we can see, let me try to get a pointer. You can see that all the democracy variables are here, and that we, on the high values of variable 1, we have non-democracies, and low values, we have non-democracies. And in this range, it's all non-democracies. So in a way, if you had this data, you could predict very precisely where the democracies are. And yet, when we run a linear regression, this will be hard to see. So when we run a linear model, we end up with something like this. Yeah, this might be a regression model or a logistic regression. And true, above the line are far more non-democracies. Below the line are far more democracies. So this will be the decision boundary. And if we observe that a variable point is below the line, we will predict that it's a democracy. And if we observe that it's above the line, we predict that it's a non-democracy. But as you will see, there are many misclassified observations. And this is because it's not really a linear pattern that we saw in the first place. So a linear model will have difficulty dealing with that. Now, sometimes transformations are possible. We can, for example, take a square term in a linear regression. By squaring, I think this is the square of variable 1, and then including variable 2, we get a decision boundary that looks something like this. And it gets a lot better. We now have a region decision boundary that is a curve. Outside the curve, we say non-democracy. Below the curve, we say democracy. And the number of misclassified cases, these cases and these cases that are now wrongly classified, and also these cases on the other side, that number is now relatively small. But it's still not quite what we would have thought when we see the original graph. So we are going to look at a different type of shape. We're going to look at a classification that looks more like this. Because here the predictions are really pretty accurate. We have a box, and within the box are the opposite democracies, and outside the box are the non-democracies. And it's a very precise classification. Of course, this is fake data, and I made it on purpose precise. So when x1 is greater than 0.3, and x1 is less than 0.8, and x2 is less than 0.4, we have a democracy. In all other cases, we have a non-democracy. So with a linear regression, even if you transform the variables, you can never quite get at this, unless you can already guess that these are the threshold values. And you put them in as separate dummy variables, but that is not a good approach. So we want a method that searches for the space among those variables where we observe one category or another. And for that, 3 models are specifically designed. So a decision tree looks a bit like this. As I said, we can look at we see the box of the democracies exactly in that area where the variable 1 is greater than 0.3, it is less than 0.8, and the second variable is less than 0.4. So we can make a decision boundary where this is a decision, and then we decide whether it's this, and then we decide whether it's this, and then we know whether it's a democracy or non-democracy. And if you wanted to make that in the decision tree, it looks something like this. If x1 is greater than 0.3, and x2 is greater than 0.4, and x1 is less than 0.8, then it should be a democracy. If x1 is greater than 0.3, and x2 is greater than less than 0.4, then it's a non-democracy. So we can seal off these different routes to decide whether we have a democracy or a non-democracy. Now there seems to be a typo here, unfortunately. So let me fix that. So this should of course be less than. Less than. Because it was under this line. So if x1 is greater than 0.3, x2 is less than 0.4, x1 is less than 0.8, then we have a democracy. If x1 is greater than 0.3, x2 is less than 0.4, but x1 is also greater than 0.8, then it's a non-democracy. If it is above the box, x1 is greater than 0.3, but x2 is greater than 0.4, then it's also a non-democracy. So we can make a decision using a tree like this. So the tree classification model does exactly this. It splits the space in two. Let me remove the drawings. It splits the space in two. Every time on the one side, it has a higher probability of non-democracy or democracy. On the other side, it has a lower probability. So for example, we can first split the entire area into 2 areas, where the variable 1 is greater than 0.3 and where it is less than 0.3. As a second step, we might divide the part on the right of that line in 2 parts again, where variable 2 is greater than 0.4 and where it is less than 0.4. And in the third step, in the final step of the classification tree, we can divide the space below that line on the right into a half where the democracies are and the part where the democracies are not. So this looks exactly like the decision tree. Is it greater than 0.3, yes or no? Is it less than 0.4, yes or no? Is it less than 0.8, yes or no? And then for each of those endpoints, each of these decision points, we can decide whether it is probably a democracy or probably a non-democracy. This is a stylistic example which has very precise data that fits very well. This is of course not normally the case, But in the homework assignments, you will see some other examples in the lab. So. Now, in R, it's relatively straightforward to do, and you get the decision tree that looks much like the one that we saw in the slides. So we use the rpart library. There is also a tree library which does something very similar, almost identical. But the tree library, the plots are a little bit harder to read. The rpart has much nicer plots that show clearer how to read the tree. So we prefer rpart. It also has a slightly different algorithm to do the classification. So if you use the tree library, right, so you could also have done library tree and then run the model with tree instead of with rpart. If you had used that version, then you will get slightly different results. So you open the library for the tree function and then a separate library for making plots that are quite readable. Then we run the rpart command here that will, with the dependent variable here and the independent variables here. And then we save the output of that command here as t. We can of course put any name we want here. This always means to save the output. So we run rpart with the dependent variable y, independent variables x1 and x2, and save the output to an object in R called t. And then we can use that object, for example, to make a table, right? In this command here, we make a table. We use the predict function, which tells you what the classification is for each observation based on the tree model. And we compare that with the original classification. So remember, we are doing supervised learning here. So this is supervised learning because we know the real classification. Yeah. Otherwise, it would be unsupervised, which we only turn to next week. So in supervised learning, we know the real classification. We put it as input in the model. We have it here in the model. And we can then also compare the prediction of the model with the original labels. Yeah, and then this is a slight technicality. It will predict probabilities for both the democracy and the non-democracies. We only want one of those, so we need to select that command. You might want to, just for yourself, type this command to see what the output looks like. And then you will see, and then maybe separately try this to see why that selection is made. And then you will be able to understand a little bit better what this command does. So this gets the predicted probabilities for each observations with the original classification and produces a table. This command in the middle here creates a plot. So this command here, rpart plot, creates exactly this plot. And so here, this one we can quite easily read. It's relatively straightforward how to interpret this because it's exactly like the decision diagram we had earlier. So if x2 is less than 0.4, yes, we go to left, no, we go to right. Is x1 greater or equal to 0.29? Yes, we go left, no, we go right. If x1 is less than 0.67, yes, we go left, no, we go right. Remember that in the data generation, the true values that I used when I generated the data was 0.4, 0.3, and 0.8. So it's reasonably close, the last one a little bit weaker. Here, in this first box, it says that we predict a non-democracy, because if we don't know anything about any of the variables, as you will maybe remember, let me go back to the diagram. If we don't know anything, we have far more non-democracies here than democracies. So if we don't know any decision boundary and we had to guess, we would guess that it's a non-democracy. So we guess that it's a non-democracy. However, if we know that x2 is less than 0.4, we know that we're below this bar here, this horizontal bar. Here, there's far more democracies than here. So now, if we don't know anything other than this bar, we would probably predict that it's a democracy. Yeah, we predict democracy. If we then also know that x1 is greater than 0.3, there's even more democracies, and we also know that x1 is less than 0.67, then we are pretty confident. If we know that we're above this line of 0.4, this horizontal line, then we know it's not a democracy. And we also, if it is less than 0.3 on the left, we know it's a non-democracy. Now, the percentages tell you how many of the observations are in this category. So here we have all the observations. Once we split between this line above and below 0.4, then above the line we have 60% of the observations, which we think are non-democracies. Below the line we have 40% of the observations, which if we don't know anything else, we think are democracies. So you can see what percentages in each category. So in the box is 23%. On the right of the box is 7%. On the left of the box is 11%. And above the box is 59%. And then this middle number tells you the probability of observing a non-democracy in this case. It could have been a democracy. You have to look carefully which way around it is flipped. So because it's 73%, we know that 27% democracy. Yeah? For in the baseline, when we don't know anything else yet. Once we know that we are on the right and on the top, we are above this bar, then we know that we have 100% non-democracies. When we know that we are on the left here, we know that we have 66% democracy. And that's why we predict a democracy. So that is if you go below, where's the mouse? Oops. If you go below this bar, here 66, you can't see my mouse. Below this bar, here 66% is democracy, and here 27% probability. Sorry, that was before the split. Before the split, 27%. Okay. So we can see how to read this diagram, and we can see how to read the table here to get an idea of how the classification works. Remember the confusion table? This is more or less like a confusion table. We predict either no democracy, or certainly democracy, or 60% chance of democracy. And then of those cases where we don't predict a democracy, they're all non-democracies. Where we predict a democracy, they're all democracies. Where we say a 60% chance of democracies, we have 4 democracies and 3 non-democracies. Then what I think is the final slide for this part. Oh no, there's a sort of pros and cons. One more step in the tree model is that we often have too many branches. If we, in the example that I just gave you, we have 2 variables, x1 and x2. In practice, you tend to have many variables. In fact, tree models are particularly nice when you have many variables. It is very good at selecting the variables that are relevant and showing which ones are less relevant. But the problem with many variables and many splits is that you get a long tree that is very difficult to read. And also, it will be very much fine-tuned to the specific data set that you have. It will know in detail exactly where to split on which variables to get slightly variation in these groups, where one has a slightly higher probability of democracy, the other slightly lower. But of course, this depends far too much on the data set. You use the same tree model on new data that comes in, and you will probably get a very poor prediction. What is a democracy and what is not? This is what is called overfitting. Overfitting is a model that is very good at predicting the observations that you have, that is very much fine-tuned to the data set you're looking at, but that does not tell you much about other data sets that can't be generalized because it is too much fine-tuned. So to reduce that, we prune the tree. We keep with the analogy of trees. We cut some branches off, so we get to the core branches, the main splits that are relevant, and not all the fine-tuning. In R, this is straightforward. We take the T object that we saved before. Remember that we saved it as T, so that is here. We prune it. This is a parameter that tells you a bit how much to prune. It can be something like 0 or minus, and it can be a small value positive. And we save it again as a new object T. And we can plot and make tables in exactly the same way. So now we have a much simpler tree. We have only one split here. We have only one split. So the main split here really is whether x2 is less than 0.4 or not. If it is, probably a democracy. If it's not, probably not a democracy. We don't need all that much more precision. So we get a reasonably good confusion matrix. But of course, this is still a fair number of misclassifications. But this is much easier to read, much easier to follow. The prediction goes down, but the generalization goes up. So we will be more likely to predict reasonably well if we use this model in other data sets than if we use a model that is really fine-tuned to the specific data we have. So when we compare the regressions and the trees, then the trees are really quite easy to interpret. They are easier to explain than regression coefficients. But then what it means to have a positive or a negative effect, what these stars for statistical significance mean, how big is an effect, especially with logistic regression, difficult to identify. With trees, we can see quite easily how to read the diagram and what this then means. It aligns much more with how we think about decisions, right? So these kind of decision diagrams, like is it less than 0.4, yes or no? Is it more ethically fractionalized, yes or no? Is it an oil state, yes or no? This is kind of how we like to think about decisions, how we can classify. It's also easy to visualize. We can make these decision trees and they're easy to handle. It can handle very well categorical variables, multiple category variables, regression variables, skill variables, very easy. So these are all great advantages of regression trees. There are some disadvantages though. It's not generally as accurate in predictions as some of the other methods. And it can lead to overfitting quite easily, so that it is less robust, both through small changes in the data and also in terms of predicting beyond the data set that you have. So trees are nice for interpretation, but maybe a little bit, they have weaknesses there. It is also more difficult to add proper control variables if you want to do more causal inference. So this is good for prediction. It really is not so suitable for causal inference. So I will stop the lecture here and we'll continue in a separate video talking about random forests, which deal a little bit with this issue of robustness and generalizability.